There are three main types of discontinuous functions, but how can we apply the limit definition of continuity to show that these functions are actually discontinuous? First, we'll take a look at one of the most obvious discontinuities, called infinite or asymptotic discontinuities, obviously characterized by the asymptote that exists in the function. Using our limit definition of continuity, we see that the limit approaching a from the left doesn't equal the limit approaching a from the right. Also, since there is an asymptote at a, f of a doesn't even exist. This function fails the limit definition of continuity in all aspects and is thus very clearly not continuous. Second, we'll look at a jump discontinuity. This can also be visually characterized by the clear jump you see in the function. With our limit definition of continuity, you can clearly see that the left and right-handed limits are not equal to each other, so even though f of a is equal to the right limit, the fact that this function fails one of the requirements means that it is not continuous. Third, we have a removable discontinuity, and it is perhaps the type of discontinuity that is mathematically and visually the closest to looking like it is continuous. But let's see why it isn't. The limit of the function approaching from the left is actually equal to the limit of the function approaching from the right. So a big requirement actually is met. However, we also notice the point here at a is empty, meaning that f of a doesn't even exist, making it impossible for either of the limits to be equal to f of a. That means the last and final requirement for continuity isn't met, and thus the function is still discontinuous. And those are the three types of discontinuity you will probably see.